Okay, here we go. Write a function P of t to model the world population growth described here. So they give you some information at the top. They tell you that in 2009, the population is 6.8 billion. Is that okay? You see that there? And it also tells you that the growth, or the rate of growth, the rate which we need is 1.133% per year. Okay. And they're trying to help you out by saying, here is some samples of what's happening. They're trying to say, okay, well, in 2011, they're saying that you have the 6.8 that you started with, but you have a value of 2 here because 2011 is 2 years later than 2009. 2012 is 3 years later than 2009. The other thing you're going to notice is that this number here, this percentage, has been converted to a decimal inside here. So you convert it to a decimal by dividing by 100, which moves the decimal to the left 2 places. Like that. But then you might be saying, well, why is there a 1 there? Well, because there's a bit more. So this is just kind of all the startup here. The function that you're looking for is the initial amount. So sometimes they go like T0, 1 plus R to the power of T.
Yeah.
Okay. And it looks like a lot, but you actually have most of these values. P0 is 6.8. R is 0.01133. And T is actually your variable. We have to define the T. So when it says, don't forget to identify your variables, your teacher's saying T represents, or T is, it's not the year, it's the number of years since 2009. Because you're not putting like 2011 here, 2012, you're putting the number of years.
Is that the answer to number 2?
We're gonna get that. Yeah, we'll get to that. Okay. Yeah, you are, yes. The answer is yes, but let's finish with number 1. Number of years since 2009. So for number 1, your teacher is looking for something like this with some amount of work that represents, something that we've put on here that kind of says, okay, I got it.
Okay. It's like a Google form thing, so I'll just like type it in.
Okay, absolutely. And that is good to know.
Also, I'm so sorry, but I have like such bad allergies and I like cannot breathe. So
I'm not noticing anything. And
okay.
if you feel like you want to mute yourself because you're just like, it's not a bother to me, and I make sure you're comfortable. I know what it's like. I actually have to mute myself every once in a while to sneeze because I'm having the same problem.
Yeah.
So
Okay, I'm good for
all right.
2.
Number 2. So we kind of just answered this. T represents the number of years since 2009. So T equals 0 is 2009. It's the base, what's called the base year. Is that okay?
Yeah, I got it.
All right. Now it says, how would you represent 1980? And we need a little bit better definition of T. T is the year minus 2009. Okay, so when the current year is 2009, 2009 minus 2009 is 0. That's what we talked about in the previous problem. Or when the current year was 2011, 2011 minus 2009 was 2. So for 1980, well, 1980 minus 2009 is 39. No, 29, negative 29. That's terrible. Negative 29. Okay. And it seems odd, but you can go backwards in these population models. Okay, now forgive me, there is one other thing that we need to do up here in P of T. P of T is in billions it's in billions. When we get an answer from this P of T, it's in billions. And I don't know if you need to, because it does say in question 1 to identify your variables. P of T is the population in billions.
So I should put that in for 1.
I think you should add that. Yeah, it would be it's probably what, because it does come up here in question 4, and it's important to kind of give them what they're expecting. It's probably expecting that, or she.
Okay, got it.
All right. Okay, next thing here is to use your model. Use your model to find the population in 1980. So we're going to use our equation P of T equals 6.8, 1 point, grab it here. This equation right there, 1.01133 to the power of T. We're going to put T equals minus 29 into the equation. So P of minus 29 equals 6.8, 1.01133 to the minus 29 power. So you got to go to your favorite calculator and calculate this.
Okay.
Let me know when you've got a value here.
Okay. Yeah, hold on. I'm not using like the right calculator that I normally use, but I got negative 22.1229.
Okay, so that's
I
that.
don't know if
Yeah,
that's right.
in your wides to say that doesn't seem right, Matthew. That's like, so I dropped in the chat the Desmos Scientific. Assuming you're on some sort of internet capable device, which you must be for the Zoom, you can definitely get there. I would recommend using this. It's really important that you be able to enter this in the calculator, because we'll probably be doing a few more calculations tonight.
Okay,
You
I
can
did it
enter it.
again on my like normal calculator and I got 4.9.
Good. Now, here's the problem with what you have there. That's in billions. So you have to multiply
Oh.
your answer by 10 to the 9th. Okay. And the reason is that will then give you the actual humans.
I got 490472987875.
Right. So we have to now write that number out. Okay. With and so I'll do it down here. It's 4904729. Did you have something after the 8?
875.
Yeah, 875. Okay. So now we can put commas, 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 and that's the actual number of people
Okay.
that our model is estimating.
Mm-hmm.
So that what's unclear is like your answer was correct. It is 4.9 billion, but that could be off plus or minus a lot. Being off by a
Yeah.
billion is a lot of. So
Yeah.
now the next part, it says, how does your model's derived population for 1980 compare? Basically, you want to decide whether what your answer is it an over or an underestimate? So the yellow is the actual. Up here at the top, this is the actual.
Okay.
And what you have is the predicted. Is the predicted too big or too small?
It's too big.
So we call that an overestimate. So your instructor is looking for the answer plus the word like this is an overestimate. All right, now do you have a TI 83, 84?
I have a Casio.
Oh, Casio. Okay, Casios are great. They're just not the standard one that most students use. So I'm not as familiar with how to use a Casio. So I'm
I
going to
also have
suggest,
a TI 83,
okay, I can show
which
you
I
how to
don't
do
know if
this
it's
in
better.
yeah, I can show you how to do this in a TI 83, or we can use the Desmos scientific calculator that's online. Which would you prefer?
We can just use the calculator.
Okay, give me a moment here to get mine opened up. And then I'll switch over to that and show
Well,
you how to.
maybe we should do it on the Desmos because I don't know if I have to like turn that in for it because it like says I have to like verify I made a table.
Right, we're going to make a table on the calculator is what I was going to show you how
Okay.
to do that rather than
But I
doing
don't
it.
know if I need to like turn that in.
Well, we're going to actually make a table. Like your result is a table. So, okay, let's just do the Desmos scientific. So let me go and new share this and see if you like it or not. All right, so here's what we've said. We said T is minus 29. And then we wrote our formula. We wrote population equals 6.8 times, or let me put in parentheses, 1.01133 the power of T. And that's how we calculated the 4.9. Okay. So in your other screen, what we want to do is build a table where in one column there's the value of T and P of T is in the other column. All right, so let me try to show you that here in the other screen. All right, so what I'm showing you here is we're gonna put in this value of T, which is minus 29, and we might even add in a column that says year. This is year 1980.
Mhm.
And then we had 4.9047, I'll just say billion. Okay.
Okay.
And then we want to go 5 years later. So that's 1985. That's minus 25. 1980 is minus 20, and so on. We're going to do this all the way up to, sorry, 1990. And so on. We're going to go 1995 minus 15, and so on. 2000 minus 10, 2005, 2010 is 0. That doesn't seem right. What's going on here? Okay, I'm sorry. I got these off. Minus 24, minus 19, minus 14, minus 9, minus 4, positive 1. And then we have to keep going all the way up. 2015 is 6, 2020 is 11. Okay, and then so on. So 2030, 2035, and then 2040. Okay. And then we're going to use the calculator and just change the value of t and record the answer here each time. Is that clear what we're doing?
Yeah. Can you give me a sec to write down the graph?
Sure. Sure.
What year do we go to?
I'm sorry, say that again.
What year does the table stop at?
It stops at 2040.
Okay.
It's kind of a mess.
Uh.
A long table.
Yeah. Okay, got it.
Good. So now what I'm going to do next is I'm going to go back to the calculator and just change the t value and record these numbers. So I would recommend you do the same because I can't simultaneously share the screens. So I'll go back to that one. One of the advantages of using the TI-83 is it would actually do the calculations. We have to do it kind of manually here, but notice I'm just changing that number to 24, and now it's 5.1890. And I'm just choosing arbitrarily to go out 4 decimal places. That's totally up to you. 5.4896. Oops, I gotta go to the right number. 19. I just did that. 14. Okay. 5.8078 minus 9, 6.1443, 6.5004, 6.8770, 7.2756, 7.6972, 8.1432, 8.6151, 9.1143, and last one, 9.6425. All right, so I got all those written down on the screen. Let me go back to that. All right, so that takes care of making a table.
Mm-hmm.
And that's it for, so 6 is maybe a different problem. Gonna restart. I don't know.
Maybe. I think so.
Wonder if this is like consuming all resources problem. We have too many people on the planet, right?
Yeah.
All right. Earth has a surface area of 196,940,400 square miles, slightly less than a perfect ball with a diameter of 7,913.5 miles, which is the mean diameter of the Earth. All right. So, graphically here, if this is the Earth, they're saying the diameter is 7,913.5 miles. The surface area is the tennis ball, the outside of the tennis ball here.
Yeah.
The surface area of the 7 continents, that's the next part here. So let me snip that in. The surface area of the 7 continents and all the islands of the world is about 57 million miles. So the whole surface area is 196 million, and the actual land is 57 million. While the total area of the 6 habitable continents, basically the places where people live, is 52 million square miles. All right. There's a lot of buildup here to the actual question. You'll get instructors in college like this where they do a lot of words and then they finally get to the question. So they say, including Antarctica, over 1/5 of the globe's land mass is underwater. Oceans, lakes, rivers, etc., or ice. This leaves about 45 million square miles of exposed land. 1 square mile equals how many square feet? Okay, we know that 1 foot, I'm sorry, 1 mile, not 1 foot. 1 mile is 5,280 feet. Okay, so if you square both, you get the number of feet squared. So you just have to square 5,280 to get that result. But I think there's more. That's just sort of a lead in for the next question. All right, so it's 28,878,400, like that.
Okay. Well,
So it says determine how many square feet of exposed land is on Earth. There are 45 million, 45, 1, 2, 3, 4, 5, 6 zeros, square miles, so miles squared of exposed land. And we know that 1 mile squared is 28,878,400 feet squared.
okay.
So this is we need to multiply. This is a huge number, so it's going to be in scientific notation. So that's like, to keep that in mind. You're not going to get away from that, but so the answer here that I've got is 1 point. We're at quite a few decimal places because we're going to need them in the next part. So that's the number of square feet of exposed land on Earth.
Okay. Then the like online thing, it says 2,788 7,800 square feet are in 1 square mile. So
Okay.
I don't know if it like he like did it wrong or if like that's what I'm supposed to use instead.
Yeah. Well, I mean, this is kind of the standard conversion here. I would double check that I've squared it correctly. It sounds like you're using some sort of like Google convert
Well, that's just
square
like what
mile.
he put in like the question
Okay.
on like the online because I thought it was just like the same.
I mean, we're talking, yeah, I mean, did I just not write the number down? Maybe I didn't write the number down. Yeah, I just didn't write the number down. It's 27, not 28.
Okay.
That's the issue. And then that does change this other one as well. Although I think this number is okay, 5,280. I just wrote the wrong number down. This calculation is correct.
I got 1.252278.
Yeah, well, you can choose whichever number you want to use. It doesn't matter.
Okay.
Because we're dealing with such large numbers, it like you're it's like when you play tennis, does the serve, if let's just say you're serving 90 miles per hour, doesn't matter whether it's 90.1 or 90.2, it's all the same.
Yeah.
So at this point,
Okay.
you got that, you got to kind of decide what you want to use. The next thing is to multiply that by the 45 million. And you can go out as many decimal places as you want on that, as you have. I've got 6 in my answer. All right. So the next step here, this is that where we go on to the 7 is kind of the whole point of this, which is like, okay, there's a certain amount of habitable
Wait,
land.
for 6, did you get 5.6352? 5?
I'm going with, there's about 45 million square miles of exposed land. There's 45 million miles of exposed land. That's miles squared. We know that 1 square mile is 27,878 400 feet squared. So when you multiply these together, this is the result that I'm seeing.
Just 45 million?
You're multiplying the given square miles of exposed land. That's this number here, 45 million. This is
Yeah.
45 million. And then you convert using this number. 1 square mile is the conversion factor. So you got, let me see here. I really like that pen. I do have a green. Okay. So the conversion factor is here.
Yeah.
So that's what I'm seeing. Then my result, I mean, you'll try it on another calculator. I mean, we got
It's just
45
like the
million.
1.254. Like, is that thing just like the answer?
Well, it's the answer in square feet. Yes, it's 1.254 times 10 to the 15th feet squared. Like, okay, if you're asking what to put in the box, I mean that's this other part here. That's the thing at the bottom. Let me circle box that in. This is what goes in the box.
Okay.
Let me know when you're ready for us to move on to 7.
Okay. I got it.
Okay, now the next part is the kind of the interaction between the answer from 6 and the answer from kind of the answer from this one here. So we're looking at a situation. It says remember, sardine packing for humans is about 1 square foot per person. So they're saying, like, imagine everyone was standing next to each other.
Yeah.
Like, you take up 1 square foot when you're standing there. Okay. And so they're asking, how many years until we get to this point? So they're asking, when does your model P of T equal 1.254 times 10 to the 15? When is the population that many people? Okay, so we got to go back to our equation. Our equation was 6.8, 1.01133 to the power of T. But remember, this was in billions. And this right here, this P of T is already kind of worked out to where it's not in extended units. So we want to add a little multiplier here of 10 to the 9th, so that whatever number we get from t, we get in terms of real people, billions. That was what we did in like part. Let me look again in question 4, where we had to convert the answer from billions to number of people. That's why it's 10 to the 9th. That's why it's saying, remember, your model's in terms of billions. So they're trying to help you out here. You're setting that equal to 1.254 528 times 10 to the 15th. All right, so we're essentially now solving for t. So to do that, you divide both sides by the 6.8 times 10 to the 9th. Over 6.8 times 10 to the 9th, like that. So we'll get some number there. And then you remember from class how to undo this, how to undo a variable out of the exponent?
Kind of.
So it's logarithms. Hopefully you've seen that before. When you take the logarithm of, sorry?
I have, yeah.
Okay, fantastic. So what the logarithms allow you to do is bring that variable out in front. The exponent comes out in front. So it's t natural log 1.01133, but it equals the natural log of everything that we still haven't calculated yet. I know it's like, when are we going to calculate that? We're going to do it at the end because there's so much here. And then to solve for t, you divide by the natural log 1.01133. Okay, so this can be entered in the calculator altogether. It is kind of a lot, but it can be done.
I can try.
Yeah, it's not. So if you need some intermediate results, I'm going to have them here for you to double check.
I got 1.548565223.
Is that for your final answer or intermediate one?
Final answer.
Okay. So there's definitely a calculation. That's what I was hoping maybe you could tell me what any of these intermediate ones are. But if you're not, that's okay. The value I'm getting here, and I can show you that in the screen if you want, but it's 1076 for t. And it's important to kind of do it in pieces. Like first do this right here. This would be a check. Let's see if this is correct. Then to do, the natural log of this, then to divide by the natural log. If you're off by parentheses, it will be problematic.
Yeah.
So this means in terms of the year though, and this is kind of important, the year is 2009 plus 1076. So hard to believe, but in 3075, sorry, 3085,
Okay.
which is it's horrible, right? It's a long ways away. But there are people that are worried about the population increase. I'm not going to be around to then, so I don't really know. It also precludes the possibility that we could live on the water or in space or in high-rise buildings, so we're not on top of each other.
Yeah.
But that's the nature of this problem. Now, number eight is to basically redo 7. It's to redo 7, but instead of using 1.133% to use 2%. So what does that mean for you? It means that anywhere you see a 1.01133, that value gets changed. Just that part though. So let me grab this where it's affected. All right. And so let me first do this. Let me go to the other calculator and show you that calculation so you can see it. Right, so down here at the bottom, that's where the 1076 came from. You can see I don't have the 1.254 in the numerator, but it's this calculation in the top, which we can check, if we need to. It's up here, times 45 times 10 to the 6th. There's the 1.25428 like you're looking for. So for you, the only change is to this right here, the 1.133. It becomes 2 like that, 1.02. So that's the only change. And you can see it went from 1076 to 612 years, which is pretty substantial.
Yeah.
All right, so let's go back to the other screen. And so all the only change that I made is that is now 1.02. And then this becomes approximately 612 years. Or you can say the year is 2009 plus 612 or 2621, which I will definitely not be around then. Maybe you got a head start, maybe you'll be around then because it'll be.
I don't think so, but
Yeah, I mean,
I
cryogenic freezing, I don't know.
something.
Something. All right, well, that I believe is everything in your project, unless there's like another page you needed to send.
No, that's it.
Okay. We've got some time left here if you would like to use it. Is there anything else you'd like us to work on tonight?
Could we work maybe more on like exponential graph stuff, because I don't really understand like that whole
Yeah,
thing.
I think that's a good idea here. So one of the things it's not been made clear is that you're solving problems that are in this form, e times a to the power of t. And a is what's called a growth factor. Or it's called a decay factor. Because things can either grow or decay. So if it's growth, it's 1 plus r. If it's decay, it's 1 minus r.
Okay, yeah, I learned that in class.
Good. And so what I'm doing, what I'm looking here for now are some questions. Where we can actually look at some situations to decide what's going on here. So yeah, here we go. All right, so here's a question for you to think about. The population of a small town was 3,600 people in 2005. the population increases by 4% annually. Okay. So when you see a problem like this, you want to think, okay, it's exponential because this is a percentage. Percentage is a pretty good indicator that it's exponential. Okay. Now, is it growing or decaying? Well, that's established by this word, right? Increases. And this is the value of R. Okay, so to write the equation for this, P of T, it's the amount that you're starting with, 3,600. Instead of A, we're going to write 1 plus the growth rate, which is 0.04 to the power of T.
Okay.
Now you should combine these numbers. So you should add what's inside parentheses here, 1.04 to the power of T, like that. And then the other thing is to indicate that T is the number of years since the base year.
Mm-hmm.
It's always the base year. All right. So
Yeah.
I want to give you a problem like this, and I want you to be I want you to try to write the equation.
Okay.
But let me see if I can find one that's similar. This is the best I can do. Unfortunately, it's not exactly the same, but we'll see. Okay, here we go. Here is a new problem. Go ahead and try to write the equation. Ask me some questions if you're unsure.
Is it 9 parentheses 1.015 exponent T?
But not too bad. Once you kind of figure it out, if you're comfortable with this. Now, there's also scenarios where things go down, right? And we see this, in various forms here. Here's an example. It says you bought $2,000 worth of stock in 2012. The value of stocks has been decreasing by 10% each year. This is 2001 minus 0.1 to the power of T, or 2000 times 0.9 to the power of T, like that. Okay.
Mm-hmm.
All right. So essentially what you can do, sorry, go ahead.
Oh, I said that just makes sense.
Yes. You can look at just the number inside parentheses and decide whether it's growth or decay. So what I've done here, what I'm about to do is snip in a bunch of problems here. If we look at just the number inside parentheses, 1.3, we know that that's growth. 0.98 is decay, right? 1.25 is growth. This is decay. Even if it was like 1.00000001, it's still growth.
Yeah.
Because it's bigger than 1.
Okay.
Okay. Any questions on that so far? For what we've been doing?
No, that makes sense.
Okay. So this kind of leads to problems where you want to find the population or figure out what's going on in in a town. That's kind of what we're doing tonight here. So let me snip in a problem like that. So it says town with a population of 5,000 grows 3% per year. Find the population at the end of 10 years. So really there's kind of an intermediate thing here, which is to write the equation and then use the equation to find the population. All right. So could you give me the equation for this, please?
Yeah. is it 5,000 parentheses 1.03 to the exponent of 10?
So that, yeah, the equation would be t, and then if you wanted it in 10 years, it would be 10. Okay.
Okay.
All right. So good. Could you calculate that for us, please, and round to the nearest human? We only want full humans in our answer.
I got 671, 6719.581.
So round to the nearest human.
Oh,
One to the ones place.
so 6720.
Yes. And whether that's reasonable or not, we don't know, but that is what 3% means. Okay. So the main kind of takeaway is this whole like growth, the factor, whether it's growth or decay, you add and then subtract and go from there.
Okay.
All right. Well, I think that's going to do it for us for tonight.